All right, welcome everyone. I talk briefly about a topic which bothers me since, well, in terms of modeling, 5 years, and it's also continuing project. It's very simple. How many ice crystals are in an Arctic mixed phase cloud? And that's very important because the amount of ice crystals in the mixed phase cloud defines the supercooled liquid fraction and the ice crystal fraction, and that defines the climatic impact of that cloud. The cloud mostly heating or cooling. And of course, in the Arctic amplification is then the motivation to study these clouds. And of course, it's an although there's NASA GIST folks involved, and Friedland and Ackermann. Of course, my student, Ichia Soon, Nicole Riemer, our former colleague of SoMAS, is involved, and folks at PNNL, Pacific Northwest National Laboratories, Israel Silver. So I cut right to the chase. I'm a laboratory guy, so I ventured into this modeling. And I would say this is the simplest mixed phase cloud we have in record in our community. It's a Sheba case. It's a mixed phase cloud, just 500 meters above sea ice. Ocean is closed, no sea spray, no additional aerosols. And for over 14 hours, it continuously produces ice crystals in very low concentrations. Mostly cloud droplets. There's no secondary ice formation. There's no Beerschot-Wegner-Findeisen process to consider. And you cannot explain the simplest cloud. So if you don't get the ice crystals here right, I don't need to look at any other clouds, which are much more complicated. And that's the motivation. A lot of LES studies and Anne Friedland and others have pointed out, if you use a typical parameterization in our community, the cloud dies out in an hour or so, makes no ice anymore. And I show that. And so we went back to this case trying to use an LES-informed model to study different immersion freezing parameterizations to get the ice crystal number right, starting from aerosol particles. The gist from that is, and we can point that to 2-3 people, that since the 1950s, what the community is doing is parameterizing ice in a way saying, well, it's time independent, it's instantaneous, and these are unique particles, meaning 1 in 100,000 makes ice. And you hear that 1,000 times at HEU, and therefore it's the grandest challenge in atmospheric sciences, the most complicated process, and we have to find this unique INPs. I say exactly the opposite. It's the most boring and simplest process. But it is parameterized in a way just with a number fraction. You have 100 aerosol particles, all one make ice at a certain temperature. Or we scale it with the surface area of the particles, also again, instantaneous. And the interpretations, each is unique, even though it's the same analytically great material. If I make 100 particles of the same material, the first one which nucleates ice is a special one. It's different than the others, although it's 99.9999% the same material. No one has proven that. This is just ad hoc. Okay, it's not scientific, let's say. The theory of nucleation is classical nucleation theory. Everyone who studies crystallization process uses this is the only theory. This is no theories. This is a parameterization. That says nucleation is random, stochastic, because of the fluctuation of the hydrogen bonding network, which goes in picoseconds. And it also scales with the surface area of the isolated particle. So you have random, time-dependent versus non-time-dependent, instantaneous. And so the big question is, how does that affect the model results? And Krupacher, as a matter of fact, warned us in the 1950s not to do this. So the community is doing that in 70 years. Also, Vonnegut already knew you have to do it randomly. And you see that in experiments. Here are 20 little micrometer-sized ammonium sulfate crystals on the substrate. We had zero conditions, -50, -60 degrees. The beauty is you can repeat the same sample all over again. And I just highlighted which particle nucleates ice the first time. That's the only repetition. But every time you repeat it, it's a different particle. So 99% of my colleagues in the community would say, no, according to this, always the same particle has to nucleate ice. All physicists in the world say, no, it has to be random. And so we want to test that. And we use an LES-informed Arctic mixed phase cloud model. We start with aerosols, very fundamental. and let the aerosol define everything in the cloud, sedimentation rate, entrainment rate, all that. I'm not going through that. The gist of it is prognostic IMP treatment. We look at sources and sinks of IMPs, because if an IMP makes an ice crystal, the ice crystal falls out, it's not in the cloud anymore. And if there are no sources of IMPs, what's happening then? And that is usually not done in our community, it's all diagnosed. So for this deterministic, this unphysical description, it's very difficult to do that prognostically, because here, these are the same particles, analytically great, the same mineral dust, water around it. At the lowest temperature of the cloud, let's say 3 particles make ice. And so according to the community, these are the special unique IMPs. So if you model that, what it means is you have to track all of them, because it's instantaneous. If your model air mass reaches the temperature, you switch on ice nucleation. Meaning you have 1 million particles, you have to track for each particle the freezing temperature. It's really cumbersome. It's a huge memory overhead. Therefore, we do it only 1D to do that quantitatively. And if it's size and temperature, you have huge 2D array, 2D arrays. You carry the whole time with you throughout the 100,000s of particles in your simulation. Hence, there is, in principle, no model which properly models INPs in a prognostic way. So we limit it to 1D. But now if you do physics, classical nucleation theory, it's just the rate. I don't need to track the particles. Why? Because I have the same particles, same material, and I apply the surface area of these particles, 3 nuclei, but I don't claim they are unique. The physics does not claim they are unique. Any of them has to go if the rate is fast enough. Yeah? You get the same number, but the interpretation is very different. And I always say, it's a little bit like lifetime calculation. If you say, what's the lifetime of methane? The more OH you have, the shorter is the lifetime of methane. But you never ask which OH molecule reacted. You never ask that because it's a second order process. And nucleation is also a second order process. We don't ask which one nucleates. We have a rate. And if you have a rate, you don't need to track. And so not only is it physically more correct, but it's also orders of magnitude computationally cheaper. We don't have these arrays in our model. So the gist of it, and that's the main figure, we try to outline that, and that's really more philosophically conceptual, changing how we look at evolution of clouds. This is a picture of what we do right now. We have our Shaver cloud, ice sheet, and all these black dots are the same exact dust particles, same radius, everything exact. We go in the parameterization, and all the orange ones are the unique ones, which potentially, if they go in the cloud, make an ice crystal and then fall out and are gone. And many studies have shown if you do it like that, after an hour, because you have a fast mixing in 30 minutes, all of the special ones saw the lowest temperature, they made ice fall out, done. The cloud dies out. And that's an unresolved problem for 18 years. We are not able to model this simple cloud. Now, if we use classical nucleation theory, the perception completely changes, because these are the same dust. So any of them can be an IMP. We don't claim they're unique. Anyone is potentially activatable IMP. We needed new phrases for that in this publication. So they go in, we apply the rate, and they nucleate. And so what you see, the cloud can draw, that's also a new term now, on a much greater INP reservoir than in this. The INP reservoir, only the few orange ones here, all of the same particles are the INP reservoir. That's idealistic, of course. In the real atmosphere, you do that for soot, for sea spray, mineral dust, organic particles. Every particle type will establish its INP reservoir. But you have a much greater one, and therefore the INP reservoir sustains continuous ice crystal formation. And if you do that in an LES model without going through all these equations, we did this here for 2 simple cases, and each year my student is now doing multi-component, multiple size distributions, and many, many other variations of the cloud dynamics. But here we have monodispersed dust, small dust, large dust. Black is the INP reservoir. Red is the ice crystal number. So we should have 0.1 to 1 ice crystal per liter. That's roughly what we observe. If you do this unphysical one, in quotes, yeah, the parameterizations, you have a very small INP reservoir. Only out of the hundreds, 0.01 will make ice per liter at minus 20 degrees. They make promptly ice crystal numbers jump up, then you deplete the INP, ice crystals deplete. So you end up 3 to 4 orders of magnitude too little ice in the cloud. And therefore, modelers throw in secondary ice processes or anything else to get the ice crystal numbers up. If you use classical nucleation theory, your reservoir is large, you start making ice, and you can sustain ice crystal formation easily over 10 hours. You see a little bit of depletion, but you are in the order of magnitude of 0.1 to 1. So that has been hinted to before. Jerry Harrington, Anne Friedland, and others, they didn't do it prognostic. But that's the novelty, is do this all prognostic and have a direct comparison. And so we are trying now more on the modeling side. People like this idea and trying this. I'm collaborating with Sylvester Arabas, University of Krakow, and he is running a super particle model. Now, I'm not a specialist in that, but it's implicitly prognostic. We know about each particle. If in the particle is an ice nucleating particle, we have cloud activation, Kappa theory, or Köhler theory. We have ice nucleation in there, and we track every little detail in this model. It's computationally very expensive, but it took him 2 years to implement in this model his 2 competing ice nucleation parameterization. And we run the Shaper case here in an eddy flow simulation. You have the aerosol particles, the dust. When they are blue, they take up water, they make the mixed phase cloud. The dark squares is where your ice crystal forming. You see the ice crystal sedimented. And he shows with this model as well, you get 1 to 2 orders of magnitude more ice crystals using the physical description, which we know since the 1950s, but our community has ignored. I have only one more slide or two. Another way where you can apply that very successfully is cirrus formation by gravity waves. Albert Ansmann from the Leibniz Institute for Tropospheric Research in Germany dragged me into that. We see smoke layers over the Arctic from Northern America. It forms the cirrus cloud. You have cirrus virgas. We have ice crystal number concentrations. And he wanted to model that in a gravity wave. It's a very slow updraft. Temperature decreases, supersaturation increases, and then you make ice crystal formation. But since it's so slow, you cannot do that instantaneous with our parameterization we usually use. Use classical nucleation theory, which is time dependent, accounts for the updraft. You get the number of ice crystals formed, and then you can analyze how supersaturation changes if the ice crystals fall out. So it works very nicely also in the cirrus case. So with that, I'm done. So the choice of parameterization, I believe, will change the ice crystal numbers by orders of magnitude in your model. Something we have since 50 years a problem. We produce too little ice in models. And it goes a little bit more, it's more philosophical, because your whole picture of a cloud, how a cloud evolves, is different, because we have now an INP reservoir which completely sustains the cloud all the time. So it's a complete, you have to change your thinking about a cloud drastically. And lastly, I think we will only do prognostic treatment of INPs anymore. So the last 20 years, where most studies, also high impact studies, are diagnostic, it is clear that is not realistic anymore. Because diagnostic, what it does is every modeling time step, it looks at temperature, humidity, goes in the parameterization and adds an ice crystal. But actually you lose the INPs and ice crystals because they sediment. So you change your reservoir. And in a diagnostic model, you don't account for that. And that is very cumbersome to program and to simulate. So that will be a challenge for the community. But I think most of us have agreed that we don't do diagnostic treatment of INPs. With that, done.
For a quick question while we switch.
John. So basically what you've done is you just found a reason to make a linear production rate with time. You're just saying that your reservoir is huge for INPs. That's really the only difference.
Oh, yeah, I'm not saying I invented something new. I just go back to the physics.
But
but-
mechanistically,
Yeah, but that's.
the INPs could be, for example, yeah, it
No,
yours
no.
makes sense. It totally makes sense.
Yes.
But really, that's all it is you're saying that you have a bigger inventory, really, relative to your growth rate or your
Yeah.
formation rate.
And of course, every particle is different, you know, I'm not saying they're the same. So you have soot, and you would have to know how much soot.
So there
is
still
around.
could be variation.
Yeah, and
So
they
it could be a
compete.
combination. I
There
mean,
will be
right.
combination.
You could be making more INPs in real time. That could be a physical chemical process as well.
So for example, each year my student puts in mineral dust and sea spray and organics and soot. And so this was only dust, and so they compete the reservoirs and sustain, and then they're
You
different.
just need to find a way to get a big reservoir. Basically.
Yes,
and
but
make
the
a first
point
order
is,
process.
I bet if you go to HEU this year, everyone will say there's no big reservoir. It's the 1 in the 100,000. It's the 1 in the million. Yeah, it's always like this, and it cannot be. It rains every day, or and every raindrop comes from an ice crystal.
Yeah, why
If
are
you
they
just think
so-
about,
Yeah, that does.
yeah, but that's the point. It's an engineering thinking or a science thinking, and there is a discrepancy, and it doesn't reflect the experiments either. Therefore, it takes a lot of effort to steer the community a little bit into the other direction. Butler knew, 1950s, he has it in his textbook. Don't do this, you know, and we are doing it. It was quite interesting, actually.
Well, your community is not very smart, I guess.
Yeah.
Well, with that, or speaking, so thanks again to you.